I was 91 Uganda. Yes. The European Institute for
No, I haven't. No.
All right, this is our show. It's my great pleasure to introduce Zach Mohammadi from Google. So Zach did his PhD at Australian National University. He got his PhD in 2021, and then he moved to MIT to do a postdoc with Social Rockland. And then since last year, he's been with Google as a research scientist, Google Research, New York City. And Zach has done so many good stuff. I'm a big fan. I've read so many of his papers on bias. So he has done a lot of good work in optimization, online convex optimization, online learning, and also reinforcement learning. A lot of good works in reinforcement learning too. But today he's going to talk about something at the intersection of optimization and online learning and hopefully learning. So.
Thanks a lot, Ariane, and thanks everyone for coming. Yeah, so as Ariane said, I do work in online convex optimization, recently more RL, but sometimes I go back and forth. So this particular talk is about results from 3 recent papers, and they're all about how to make online convex optimization more practical, approaching more on the computational perspective. And as I'm going to show you, this also has implications for the non-convex setting as well, right? So basically, a lot of settings reduce online convex optimization, and so if you come up with something efficient, it has implications on all these settings that people care about in practice. Okay, so let's jump right in. I'm not sure how many of you are familiar with the OCO setting, but let's just go over it. So this is a setting where you have an algorithm that interacts with an environment, and it proceeds in rounds. In each round, the algorithm outputs some iterate WT in some convex set K. So let's assume this K is a subset of the Euclidean space. Once the algorithm outputs WT, the environment reveals some convex function Ft. So this function Ft can be chosen adversarially. So it can depend on WT as well as the past history. And the goal of the algorithm is to ensure a small regret. So when you look at the sum of the costs that the algorithm has incurred, you want to make sure that that's small compared to the best fixed action in hindsight. So the best fixed action in this case is W, which I denote in red here. And perhaps surprisingly, even if these functions Ft can be chosen adversarially, there are algorithms that can guarantee sublinear regret. So if you pick online gradient descent, you make sure that this quantity here is going to be at most root t. Okay? Okay, so that's the online convex optimization setting. Why should you care about this setting? Well, as I said, many settings in optimization reduce to OCO, and that includes standard offline convex optimization where you have a fixed function f, or the stochastic convex optimization where you have some stochastic version of the function f. And typically the goal here is to find some W hat that is a near optimal point, okay? So I'll show you like the translation from OCO to a guarantee that looks like this is very easy. It's through something called online to batch conversion. So you start with your regret in OCO, and now when you have a fixed function f, this regret, writing this inequality, you can write it equivalently in this form here, where I divide it by t. And then you can apply Jensen inequality to move this average over time inside the function f. And so now if you pick your W hat to be this average iterates, that this inequality immediately gives you a suboptimality guarantee for your W hat, right? So you can easily move from OCO guarantee to this offline thing. And so in particular, if you're trying to find an epsilon suboptimal point, then OCO gives you the number of iterations that you require is 1 over epsilon squared, right? And we know that this is optimal in general. And you can do, this actually holds for general f, like you don't even need smoothness or anything like that. If you do have smoothness, then there does exist more specialized algorithms that can allow you to achieve this faster rate. So you have beta over square root epsilon, and sigma here is just the noise in the stochastic gradient. So when the noise is 0, meaning that if you're in the offline setting, you recover fast rate, which is beta over square root epsilon, which we know is optimal for first order methods, right? So this OCO framework is very powerful. And this does not stop with the convex case. So even in the non-convex optimization, where now the goal is to find an epsilon stationary point, there has been work that showed that you can, even that setting of non-convex optimization, you can reduce it to an OCO problem, where you recover the optimal number of iterations in that setting. And you recover also like some other guarantees that were not possible before. And not only that, but also reducing it to OCO gives a framework for algorithm design. So you can actually recover like things like adding by just changing the OCO algorithm, like by setting the OCO algorithm to a specific subroutine. But it gives a more general framework for designing new algorithms, right? You can just play around with the OCO subroutine, and then that gives you like a new algorithm for non-convex optimization. So the framework is very useful. That's kind of like the message that I'm trying to convey here. But anyway, back to my point here is that OCO leads to optimal number of iterations for many optimization settings that people care about in practice. Okay. The problem is, at the end of the day, what we care about in practice is the computational cost. So sure, the number of iterations is optimal, but we care about the computational cost, which is the number of iteration times the cost per iteration, right? And the problem here is that the cost per iteration can be high whenever you have to deal with constraints, right? So whenever your iterates are outside of the set, you have to make sure that to project them or do something to them to make sure that you're playing within the feasible set, right? And handling the constraints is what is costly in general. So what, for example, if we look at online gradient descent, the algorithm, okay, let's go through the algorithm. You pick some arbitrary point in your feasible set at the beginning, then there's a for loop where you query the subgradients at the iterate. Then you update your iterate just by following the negative direction of the gradient. But now this UT plus 1 may not be in the set. You may have stepped out of the set, so you project. And so I express this online gradient descent with ft. But if you have a single f, then what you want to do after you finish this for loop is return the average iterates. So when you look at the computational cost here, the cost would be the number of iterations t times the per iteration cost. If you want to find an epsilon suboptimal point, then you need to set t to be 1 over epsilon squared. And so the total cost would be 1 over epsilon squared times this per iteration cost, right? And here cproj is the cost of performing a Euclidean projection onto the feasible set. Okay, and so this cost here can be high. If you're in the offline setting, the cost of a single projection can be as high as doing offline optimization in the first place, right? So which kind of renders going through OCO first a little bit useless, right? So we want to find algorithms that avoid this projection. That's the whole point of this talk. Yeah.
What is D?
D is the dimension of the. So we're assuming that K is in a Euclidean space, and Euclidean space is yeah. So yeah, the goal: design computationally efficient algorithm for OCO. And in particular, we want projection-free OCO algorithms. So the outline would be, I'm going to go through some existing and new results in this setup. Then I'm going to show you like a general framework that reduces constrained OCO to basically unconstrained OCO. And this framework is very versatile and can be used in many settings. But first, like if there's any question about the setup or the goal. We're all good? Okay. All right, so let's see what's out there when it comes to projection-free algorithms. So probably the most famous projection-free algorithm is something that's based on the famous Frank-Wolf algorithm. So the Frank-Wolf algorithm, instead of requiring a Euclidean projection onto the set, it requires linear optimization onto the set. So given an X, the oracle is able to return a W that minimizes this linear function. And for many settings, for many sets K, linear optimization can be much more efficient than Euclidean projection. And this has been, this came up like a long time ago, and it's been very useful since then. And so the algorithm goes as follows. Again, same as online gradient the set. You start with some point in your feasible set. You query the gradient at your iterate. And then what you do is you look at the point in the set K that maximizes this objective. And then you update your iterate W2 plus 1 by taking a mixture of the new iterate UT plus 1 and the previous iterate. It's a very simple algorithm, very nice, used in practice a lot of the times.
You can do Frank-Wolf with any convex objective, right? Not just one.
So I'm not assuming here linear, so we have FT here. So I'm taking the subgradients of FT.
Oh, sorry.
Yeah,
I see.
But everything reduces to linear at the end, right? Like, use convexity. So the problem with Frank-Wolf is that, earlier I showed you that OGD, online gradient descent, gets you a square root T regret. So Frank-Wolf does not quite get that. It gets T to the 3/4. And this regret down here has been around since 2012. It hasn't been improved upon. There is no lower bounds. We don't know if Frank-Wolf does better, but it's kind of like stuck at this T to the 3/4. And in the offline setting is also like 1 over epsilon 2 cube, which is suboptimal. And the cost per iteration is better because you pay for the cost of linear optimization instead of Euclidean projection. But the guarantee is suboptimal, right? And so, okay, that's one type of algorithm that's been around for like decades. And more recently, there's been a new type of projection-free algorithms that instead of using a linear optimization oracle, they use a membership oracle or a separation oracle. So the membership oracle is just an oracle that you give it a point X, and it tells you if that point X is within your feasible set or not. And a separation is like a stronger version of that, where not only it tells you if the point is outside, but it also gives you a separation in hyperplane, right? So there's algorithms that use that type of oracle instead of linear optimization. And finally, there's a third type of algorithm that make use of a barrier, like a self-concordant barrier for the feasible set itself. But these ones are typically also inefficient unless your set is very simple, like a Euclidean ball or something like that. So we're not going to focus on that one. We're going to focus on the separation-based algorithm. And that's kind of the novelty that I said came from like these 3 papers that I mentioned at the beginning of the talk. So if you look at the guarantees that this new class of algorithm gets you, well, this was the first projection-free algorithm that achieves a root T regret, right? There's this kappa term that I'm going to tell you what it is in a sec. But if you focus just on the dependence on T, this is optimal. And also the number of iterations to reach an epsilon suboptimal point is optimal. And the cost you pay per iteration is scales with the cost of performing separation. And again, this can be so if you have a polytope, the cost of performing separation is just going to be d times the number of linear constraints you have, right? So it can be very cheap in many settings, much cheaper than performing projection. Okay, so if you look at these guarantees, they are very close to what online gradient descent can achieve, except for this kappa term that I haven't told you about yet. So kappa here is intuitively it measures like how well conditioned the set is. Like the more round the set is, the more kappa is going to be close to 1. And essentially it measures the you look at the largest ball that is contained within the set K, and you look at the radius of that ball, and you also look at the smallest ball that contains the set, and essentially kappa is going to be the ratio between these two. And of course, this kappa can be arbitrarily large if you have an ill-conditioned set, but in the original paper we had, we showed that in many settings of interest you don't have to do anything, like kappa is less than d, which is good. But in general, as I said, it can be large. Fortunately, you can always apply an affine transformation to your set to make sure that kappa is at most d. And so the affine transformation here is like, you need to put your set into what is called the isotropic position. And when you do that, then this conditioning parameter kappa is at most d, like this is guaranteed. The downside of this is that putting the set in isotropic position costs, I don't know, 2⁴ or something like that. So even though you only have to do it at the beginning of the game and only once for each problem, like it's still a bit of an annoyance. And even if you manage to do that, so kappa can be at most d in the worst case. And so this means that the guarantees that you're going to get here are going to be d root t and d squared over epsilon squared, right? So it's not ideal, and makes you wonder if we can shave off some of these d factors. And in particular, there's two questions here. Like first, can we get rid of this need for pre-processing? Because as I said, like if you don't pre-process, kappa can be very large, and then then the regret is very large. So can we get rid of that? And the second one is, can we do better than d square root t, even in the worst case? Okay. And yeah, spoiler, the answer is yes to both of these two. And this is what we get. So this is the newest algorithm, just last month. We managed to get square root dt. Yeah.
So if the set is unbounded, the kappa probably is infinity, right?
So we're assuming the set is bounded and yeah, compact set. Yeah. Any other questions? No? Okay, so with this new algorithm, we achieve a square root dt. So there's no kappa in the main term, but there is added this like O of kd, but that's a lower order term that does not depend on t. So as t gets larger, the first square root dt is going to be the dominant term, right? And we also get the fast rates. So instead of 1 over epsilon squared, which is what OGD would get you, you get something like 1 over epsilon. I mean, albeit you have this kappa multiplying in front. But there are certainly regimes where this is much better than, for example, OGD. The cost you pay from a computational standpoint is d squared. So this d squared comes mainly from matrix vector multiplication, which is not that bad. Like they can be parallelized, and the number of calls to the separation is the same as the previous algorithm. So so you pay like the cost of performing separation once at every run. Yeah.
I thought you said 1 over epsilon squared was the optimal rate for offline optimization. How do you get to it?
Right. So those lower bounds assume that d is larger than 1 over epsilon, or something like that. So when d is larger than 1 over epsilon, then this becomes worse. But in small dimension regime, this is better. Well, also the other thing that I mentioned is in offline optimization, you can do cutting plane, you can do other things, and you pay like d log 1 over epsilon. But when I say optimal, I mean for first order methods. Technically, this is a second order method because like you need d square memory for this one. So yeah. But in stochastic optimization, this is still interesting because you cannot apply cutting plane or something like that. Okay. Any questions on this? So if no questions, then the second part of the talk would be about first this initial results, and then we're gonna move on to the second one. Okay, so let's look at how can we do projection free with separation oracle. First, some definitions. So some of you may be familiar with something called the Minkowski function, or I call here the gauge function. So this is essentially, given a point x, let's say that this point x is outside of the set, the gauge function essentially measures the amount by which you need to scale your set k to include x. So in this particular example, you need to scale your set k by 2 in order to include x. So it's the minimum amount by which you need to scale to include x. So we're going to use this gauge function later on. The good thing about this is that you can approximate it using only logarithmically many number of calls to the separation oracle, to the membership. You can just do binary search, right? Even with the membership oracle. So this is going to be very handy for the computational aspect of the algorithm. One thing I would say here is that when the set is centrally symmetric, when k equal minus k, this becomes a norm. Okay, but in general, it's not a norm. The second concept that I'm going to need is the gauge distance. It's not technically a distance, but I call it a distance because if you swap out this gamma k for the norm, then this just matches the definition of the distance. And pictorially, what this distance is, you draw a line from the origin to the point x, and you look at where in the boundary where it intersects, and that line segment, the length of that line segment is the gauge distance. And even though it has this like complicated definition, it turns out to have a closed form, a nice closed form as a function of the gauge function itself. Yeah.
So that always upper bound the projection distance?
Yes, well, yeah, I mean, projection is
Yeah,
like the smallest distance. Yeah.
And then is the sphere, like the asphericity, is that how you can control this error?
In a way. So it's gonna come up. It's gonna be clearer in a bit. Yep.
You may have a set at a point so that no matter how much you expand the set never covers. Like, I mean, if it's set somehow lower dimensional.
So I'm assuming the origin is in the set.
Sorry?
I'm assuming the origin is in the interior of the
In the
set.
strict interior.
Yeah, but you can always like shift. You can always shift the set so that it's in the interior, right? Like, yeah, the translations are fine.
No, but you need rotations as well, right? No. So, thing I'm worried about is if your set's a subspace.
Yeah. I was just
Right,
thinking of set as a
so-
plane. And
so-
X is
Right.
compact.
If it's a subspace, I guess you don't allow that.
Sure. I guess then you just do the OCO in that subspace. Yeah, I'm assuming that the interior is like non-empty.
Like
But you
strict
can
interior.
always kind of like reduce it to a problem where, yeah. Good. Okay. Okay, so the last concept we're going to need is a gauge projection. So the gauge projection naturally is just the point where this thing intersects. And it turns out to also have a very nice expression as a function of this gamma of k of x. You just take your x and you divide by gamma of k of x. Okay, so the nice thing about these two, which by the way is all we're going to need to make sure that the iterates are feasible, these two things can be approximated efficiently using separation order, using logarithmic number of calls. Okay. If there's no questions on the definitions, I'm going to show you the protocol now. So the protocol requires an OCO subroutine A that's defined over a ball that contains the set K itself. So I'm not going to specify what this is yet, but just assume you have this subroutine that's defined there. And the point here is that because it's defined on a ball, it's very easy to like we can even do projections there. You can set A to be OGD and projections are two on the ball, right? And we're gonna offload the computation for making feasibility elsewhere. Okay, so with this subroutine, the algorithm goes as follows. You query an iterate from your A, so that iterate is going to be on the ball, which may not necessarily be in the set K itself. So you need to make sure you transform it so that it's in the set. So here what we do is the gauge projection. We can take UT divided by gamma K of UT, which we know we can approximate efficiently. And now WT is guaranteed to be within the set. Then you query the gradient at the WT. And then the next step is you want to send feedback to the subroutine A, but instead of sending the gradient itself, you're going to modify the gradient a little bit. You're going to massage it, where this delta t here is the subgradient of the gauge distance. And I'm going to tell you later is that approximating the gauge function, the gauge distance is cheap, but also its subgradient is cheap. So it costs the same. It's also logarithmic in the number of constant separation.
Sorry, going back to the previous slide.
Yeah.
You said that you can approximate the gauge distance using an order one number of calls using the separation oracle.
Yes.
Is it obvious that there's no dimension dependence in that? That the constant does not depend on
There might be dependence like inside the log, but not.
It's a log D, there may be a
Something
log D
like
kind
that,
of thing, right?
Yeah. Okay, so this expression for the gradient is a little bit complicated. I'm going to give you an interpretation of it in the next slide. But for now, let's accept that definition. So the feedback that you send to the subroutine A is this modified gradient. Okay, and this is the whole subroutine. In the next few slides, we're going to see why this works. But let's see what this modified subgradient is. So if you look at the definition, we know that GT is the subgradient of F and delta T is the subgradient of the gauge distance. So the interpretation here is that G tilde is a subgradient of a regularized objective, where the regularized objective is basically like a linearization of your original function, but now you add the gauge distance. So the gauge distance is convex, okay? And it turns out that the constant that's multiplying it in this expression is also positive, as I'm going to argue. And in fact, the reason for this is, remember that UT was the output of A, which may not be in the set, but WT is just you just rescale it, right? Which means that since UT and WT are parallel, the sign of this inner product GTUT and GTWT is the same, right? And so because you have this indicator checking for less equal than 0, this whole thing is going to be non-negative. And so, yeah, in fact, this function is convex, and it can be interpreted as a regularized version of the linear loss. And yeah, like you can see it in one-dimensional case where K is just an interval. Pick your F, look at the linearized version, and essentially S is just going to be a ramp. So it's going to be 0 whenever you're inside the set, and then it's just going to grow linearly after that. Okay. So that's the interpretation of G tilde. It does not tell us why the algorithm works just yet. So the algorithm works because of this. There's particular choice of G tilde guarantees the following. It guarantees that for all rounds and for all possible W's, so W's are the comparators, you have the following inequality. So the left-hand side of this inequality is just an upper bound on instantaneous regret, just by convexity, right? Because GT is the subgradient of WT. So this is an upper bound on the instantaneous regret. The right-hand side is actually the instantaneous regret of the subroutine A itself. So because, remember, like we took UT from A and we fed G tilde to A. And so this is just by definition the instantaneous regret of A. And this holds for all T and for all W, right? Thanks to the choice G tilde that I defined here. Right? So this is a little bit magical, but the proof is actually quite simple. Like it just like falls through naturally. And why is this useful? Is because if you take these instantaneous regrets and then you sum them over rounds, then basically on the left-hand side, you get the regret of your algorithm that you care about. This is what the quantity that we want to bound. And on the right-hand side, well, this is basically the regret of algorithm A. So you probably see where this is going. Now what we can do is like, okay, I'm just going to pick A to be OGD. And I know that like projections are cheap because it's defined on the ball, right? And if I pick it to be OGD, then the regrets, I'm just going to plug in the regrets of OGD, which is just the radius of your set times the maximum norm of this modified gradients that you have. times square root t. And where this kappa comes from is exactly from here. So by the way we define this g tilde, this modified gradient, the maximum norm could be as high as kappa, right? That's how we pay for it. But that's it. So this, bounded the regressive algorithm by the regressive algorithm A, and we plugged in OGD. On the computational side, I argued that like the algorithm A itself, because it's OGD and the projections are cheap on the vol, that's going to be just order D. The other steps that require computation are computing the gauge function, computing the subgradients with the gauge function. But both of these can be done in log number of calls to the separation oracle, as I said. Okay, so a quick summary of this protocol. So you have your protocol. We need an Okra subroutine A. We know it's cheap because it's over the vol. To ensure feasibility, we need to be able to do these gauge projections, which are also cheap using a separation oracle. And the way we do it guarantees that the instantaneous regret of the algorithm is less than the instantaneous regret of the subroutine. You sum them over rounds, and then you plug in A as OGD or any of your favorite algorithms for OCO, and then you get this R kappa T. Right? Very simple, and that's how we do it. So, any questions before
Yeah, sorry, I missed. Where did the indicator function come from? Like, did I miss that?
Well, so the indicator comes from. Well, when you look at the proof of this first inequality here, that guarantees this inequality.
Yeah.
That's where we use the indicator. Like
Did you explain it or?
I did not explain.
Okay, so I didn't miss that. You just didn't
You
explain.
did not.
Oh, okay. Okay.
Yeah. We'll
Is
see if you
there,
have
is
time
there an
later.
intuition for that or?
Not that I prepared for, but maybe after I can show you. But any other questions, I guess, on the reduction? Yeah.
So A is running OGD on the F bar function.
So yeah, it can be interpreted like that because so it's receiving this G tilde T, right? So you look at the last line of this algorithm. That's the feedbacks that it gets, and G tilde is the subgradients of the F bar. Yeah. So yeah. Okay. No other questions? Okay, good. So yeah.
Yeah, so if you go back to the algorithm, so this one. So what if I pre-multiply the indicator by some constant, like some C? Like, is there like so here it's basically the constant being 1. So is this one constant optimal, or like is there a scope to optimize over that constant?
It is pretty, there's not much wiggle room for the constant itself. Yeah. I should have had some sketch proof here for why this is, but maybe for the next talk. But okay, just in the interest of time, let me move on. So the limitation of this is that, as I said earlier, the kappa can be as large as D, even if you pre-process. And the main question is, can we get rid of this kappa? So yes, we can, and basically we replace it by square root D, and kappa only appears in this lower order term, which we are happy with. And crucially, we don't require any pre-processing, we don't need to wait in isotropic position, and also the same number of calls to the separation order. Okay, so that's the last part. How much time do I have left?
10 to 10 minutes.
Okay, cool. Okay, so the starting point of this new algorithm is going to be pretty much the same as before. So we're going to start off with the same protocol. All we're going to do is change the subroutine A itself. Okay, we're going to set it to something else, like all-one Newton state. Okay, so we start off from this inequality. By the way, this inequality, as I said before, this holds regardless of this of the OCO A, of the subroutine A. As long as I set this G tilde in the right way, it does not matter what A is, this will always hold. So we're going to start off from there. And I'm going to massage this inequality a little bit. So we know that the function x that maps x to x minus eta x squared over 2, that's non-decreasing for a certain range of x. For x less than 1 over eta, this is going to be non-increasing. non-decreasing. And so if you use that, you can transform that inequality that you had initially to this new inequality that involves the squares as well of the inner products. Right, so I'm only, and this of course is going to be true for small enough data. Right? I'm not being like very precise here, but like that's, you can get this. And why this is interesting is because now if you look at the right hand side, this can be interpreted as the instantaneous regret of A with respect to now a curved loss, because you have the square inside. And in particular, this loss is what's called exp-concave. Yeah.
Sorry, I just want to mention, maybe I missed it. GTable is still the same GTable that we had in the previous one.
Yeah, it's same, exactly.
Same. You just add it in the
Exactly. Same GTL, same GT, same everything. Yeah. So far, I have not done anything different. So the right-hand side here, as I said, can be interpreted as instantaneous regret with respect to this exp-concave loss. So exp-concave here means the exponential of minus f is concave. Right? So it's weaker than strong convexity, but you know, it's somewhere in between, not like just convex and strongly convex. So if we start off from this inequality and we sum over rounds, then same as before, the right-hand side is going to be the regret of the subroutine A with respect to this exp-concave losses. And when you have exp-concave losses, we know that you can get better than square root t regret. So in particular, if you choose A to be an algorithm for exp-concave optimization, you can get a logarithmic regret. So d over eta log t. And why this is helpful is if you rearrange this, you will get this inequality. Right? The left-hand side is the regret of the algorithm. Right? So we only need to bound the right-hand side. If you tune eta, you're basically going to get the following. Without going to the details, like it's pretty easy to see like what eta here that minimizes this. And you can even also bound that to get square root eta. Right? So technically, we do have kappa d just because the range of eta for which that function is exp-concave is bounded. So that's why you get this lower order term. But this is good. So we got to square root dt just by, instead of using online gradient descent, using this algorithm that has logarithmic regret. Okay? And so, you know, now the only thing that we need to ensure is to choose an algorithm A that is efficient for exp-concave optimization.
Yeah, so that's one question, because this regret you get with online Newton's method, right? I think that has, I think that's the log t term. You can do the online Newton method of LR, right?
Yeah.
But then that you need to compute the sum of gradient returns from inverse.
You're ahead of me, like I was gonna do this slide. Okay, so the question is like, what algorithm can we use for online convex exp-concave optimization that is efficient on the ball? And as you were pointing to, even on the ball, you know, that like we don't know what to do to get something efficient. And actually, there's a code open problem on that, like how to do efficient exp-concave optimization even on the ball. But the answer is going to be here. So let's first go over online Newton step. Okay, some initialization. You pick some points in your set K. You query the gradients at your point ut, which is the iterate. Once you get your g tilde, you update the sum of the. So delta here is just the sum of the gradients. The vt is the sum of the outer product of the gradients. You can think of it as like some sort of like approximation of second order information. And then you take a Newton step. So it's basically ut minus the inverse of your second order matrix times delta t. But since this ut tilde may be outside of the set in the same way that it was outside of the set for OGD, you need to project it. But now, unlike OGD, the projection that you need to do is a little bit more complicated. So you cannot just get away with Euclidean projection. If you do Euclidean projection, you're not going to have necessary guarantees. So what you do is something called a Mahalanobis projection. So it's projection with respect to this VT matrix. And the problem with this is that even if your set is a Euclidean ball, you have to do some SVD here. And so the cost per iteration is always going to be dq, right? And that's kind of like a showstopper. So So we're not like this. This does not solve our problem. Even though it gets us the regret that is square root dt, it's not solving the problem. And the question now is, how do we avoid projections? So let's take a quick step back and then see how we can modify the online step to avoid projections. And this is actually going to be like of independent interest. You can always apply it for online exp-concave optimization to have cheap alternatives to projections. So it goes beyond this OCO set. So the Newton iterations, you can view it as it has this equivalent form where phi t plus 1 is some potential function. So this potential function is the linear function of the gradients, the sum of the gradients, and some quadratic term. Okay. So yeah, these two here were just the sum of the gradients and the sum of the outer products. So what I'm going to do here is modify this potential function to ensure that the Newton steps are always going to be in the set. And one way of doing this is adding a log barrier. Right? So I'm going to add a log barrier of the Euclidean ball. Okay. And using some magic properties of self-concordance, because this log barrier is self-concordant, you have the following very nice result. So for all u's that are inside the interior of the ball, the Newton step from that point is always going to be in the interior of the ball. This is very, very useful. And so this means that, yeah, we can just modify our all-one Newton step by adding the barrier, and suddenly all the iterations are going to be within the set, guaranteed, right? So what's the catch? There's a catch. So the catch is you need to invert the matrix. So that's d to the omega. And unfortunately, you cannot just do rank 1 updates because the log barrier itself affects a term that like multiplies a non-rank 1 matrix. So this is an issue. And yeah, d to the omega, I mean, in practice, it's like d cubed. So that's bad. So the key idea here that we're going to use is we're going to try to approximate these Hessians using Taylor expansion. And we're going to Taylor expand around a small number of Taylor expansion points. So ideally, we want like only like maybe like root t Taylor expansion points around which we're going to do the Taylor expansion. And we're only going to compute the full inverse square root t times. At a high level, this is what we're going to try to attempt. And somehow this works. So let's look at the actual protocol in more detail. So it starts off the same as ONS. And now what's different is that I'm going to approximate this inverse of the Hessian using a Taylor expansion with logarithmically many order around this ZT. I'm going to show you in a sec how this ZT is updated.
I'm sorry, I missed it. How many terms are going to
log t something. Yeah.
That's enough.
That's enough. Yeah. And actually, like to compute the expansion, it's only going to cost d squared times the number of the order. So the order is logarithmic, so it's like order d squared. And by the way, crucially here, the reason this works is because we have the ball as the feasible set. So it does not necessarily work for other sets because things become more complicated when you want to do the Taylor expansion. So for the unit for the Euclidean ball, like the expansion is very nice. Okay, then to do the Newton step, you can pick that matrix H and do the Newton step. And if your approximation is good enough, then you inherit this fact that if you are within the interior of the set, your iterate is still going to be in the interior of the set. So the way you update this Taylor expansion point is by you look if ut plus 1 is close. I'm being like vague here on purpose. You see if it's close to the previous Taylor expansion point. If it is, then you don't change the Taylor expansion point. If it is far, then you basically update the Taylor expansion point, and you then also compute you compute the full inverse of the Hessian from scratch. And so now if you look at the computational cost of this algorithm, it's going to be d squared times t. This is for the Taylor expansion part, And otherwise, it's going to be the number of times, it's going to be the cost for inverting the matrix times the number of times you've switched the stereo expansion point. Thankfully, the online Newton steady threads, we show that they are stable, meaning that they don't move too far. You know, and you can use that fact to show that you're only going to switch points at most root t times. And so this becomes the total cost of the algorithm. And so the right-hand side term becomes the lower order term, like as t gets large. And so you end up with just d square root. So that's it. So that new algorithm, like you just plug in this new online Newton step instead of A, and you get these new bounds here. As I said, crucially, you don't have kappa in the main term. And the cost is, it's logarithmically many calls to the separation oracle per round. I did not go through this fast rate result. So this one, it's not simply just an online batch-to-batch conversion from the regrets. It's a little bit more, but you know I don't have time to go through it. But it's an interesting result on its own. So in terms of open questions, probably for like most ambitious to less ambitious, can we get a dimension-free root-t regrets for any projection tree algorithm? That would be the holy grail. The other related question is like, well, this t to the 3/4, as I said, has been around for more than a decade. We don't know if there's a lower bound. We don't know if we can improve on it. Can we do something there? And maybe like least ambitious would be, can we get the square root dt that I showed you with this ONS algorithm without d square method? And yeah, so that was my talk. So any questions?
Is there any other questions for Zach?
So previously, sir, it is the number of times is changing zt plus 1 and zt.
Sure.
So there was the inverse of a matrix, like perfect inverse. So d power omega. But you said that is in practice is d cube, right?
Sure, it's d cubed times square root t. Yeah.
Doesn't that affect us? The d cube.
I mean, like for t sufficiently large, the d squared times t is still going to be the dominant term.
And
Right.
what I'm saying, that does not affect the computational cost you're saying.
Eventually, the average cost is going to be dominated by the d squared.
So I'm just wondering that even for projection-based algorithm, you can also possibly use this reduction to exp-concave technique.
Yes. Yeah.
And without really to any new results.
You will get d to d over epsilon. Yeah, something like that. Sure.
But it will be worse than the standard projection-based algorithm.
What did you say? Like even if you do projection, you can use this reduction to exp-concave optimization.
Yeah. So, you know, even if you have the projection oracle, we can also use this reduction to
Yes.
concave.
So you get d over epsilon, but like there's a regime for which that is better than 1 over epsilon squared, depending on d, right? Like if d is very large.
Epsilon is better, but they have additional dependence on the direction.
Yes.
What is an example of an optimization problem where the separation oracle is super easy, but like Frank-Wolf oracle or the
Polytope. Polytope with polynomial number of linear inequalities. So Frank-Wolf is usually like linear optimization is good when you have like some matroid polytope, like some where like linear optimization is very cheap. But people usually work with polytopes in many settings, and for that it's more natural to consider separation.
I mean, Zach is going to be around for lunch, and after that, so if you have more questions, we can chat. Thank you so much.